Welcome everyone again from my side to our today's regular webinar series, which is about the thermal characterization of nuclear materials and the instruments for radioactive samples and nuclear applications in thermal analysis. What I just told the people who were already here, during the presentation, everyone will be muted and there will be a moderated question and answer session after the presentation. If you want to have any more information, or if you have comments or you have questions, please type them in the question answer tool or type them into the chat. We will have a discussion after the presentation. For those who are facing sound issues, video issues, the webinar will be recorded and the recording can be found in the chat after the webinar, and you can also request it by mail from our colleagues where you registered. Before we start with the topic, I want to introduce myself. My name is Sebastian Seibt. I'm the head of laboratory at Linzais, Germany in our headquarters. I'm working here since 2013, and I'm mainly responsible, as said, for service measurements, test measurements, and sales support. Today I'm not alone. Today I got an expert at my side, Miss Erika Hahn, who is working with me in the lab, and she's mainly responsible for thermal conductivity and thermoelectrics in our lab. And she will introduce you the thermal conductivity instruments for nuclear applications later. Erika, if you want to say hello, you can.
Yeah, at this point also, hello from my side. Welcome everyone to the webinar.
Yeah, as said, she will introduce you the thermal conductivity instruments for nuclear applications later. Today's agenda, just briefly, I'll introduce the company to you, then I will show you our portfolio, and I'll talk about the specific instruments that were modified for nuclear applications and very corrosive atmospheres so far, which is mainly our thermal balances and STAs, dilatometers and LFAs, and then we have a short look on some applications. As said, I want to begin with a little introduction of the company. There may be some people who do not know the company yet. So a short introduction. The Linzais Messgeräte company was founded in 1957 here in Selb in Bavaria, where our headquarters is still located. We were founded by Dr. Maximilian Linzais, a physicist who worked here for a bigger company, inventing dilatometers in the 1950s and starting his own business. Meanwhile, we are belonging to his son, Mr. Klaus Linzais, and his two sons, Florian and Dr. Vincent Linzais, are in charge of the company, are our current CEOs running the daily business. Besides our headquarters, we have facilities in USA where we have a laboratory, a fully equipped laboratory for service and measurements and trainings. We have distributors and salespeople there, and we have also technicians for maintenance for the American continent there. And the same for India and the same for China, where we have laboratories and where we have staff and technicians to be quickly at the customer side if needed. In all the other countries, we have distributors and companies who are representing us. And I think it's more than 65 meanwhile. So we are really spread out all over the globe meanwhile. And there's almost no country where you cannot buy and you do not have access to a Linzais instrument if you need one. Our main business area is the manufacturing of instruments for thermal analysis, thermal conductivity analysis, and thermoelectric material characterization, which is mainly used for material research and for material science. And what we also offer is service and contract measurements in one of our laboratories worldwide. So this is what we do and who we are. Our product portfolio and product range can be found on the next slide. I'm always sorting in a little bit. So the upper line shows the so-called classic thermal analysis, which consists of differential scanning calorimetry or DSC instruments, thermal balances, which we have in multiple versions both, and then the simultaneous thermal analyzer. It's more or less the thermal analysis instrument. If somebody speaks of thermal analysis, mostly he's speaking of a simultaneous thermal analyzer, so-called STA, which is a combination of DSC and TGA, so you can measure rate change and heat flow simultaneously. Of course, also here we have multiple versions. I'll get back to the topic later a little bit. Besides that, we have multiple versions of dilatometers for measuring thermal expansion, measuring shrinkage, sinter profiles, and many more. And we have thermomechanical analyzers for Young's modulus determination, for bending experiment, and stress and strain experiments. Besides that, in the lower line, we also have a broad range for thermal conductivity and thermal diffusivity. On this picture here, you can see a LFA, so laser flash instrument, which is more or less the most famous one because it's universal. And besides that, we have multiple other techniques for thermal conductivity, like wire techniques, guarded hot plates, and heat flow meters and stuff like that. We have analyzers for thermoelectrics for measuring electrical conductivity, resistivity, Seebeck coefficient. We have instruments for the Hall coefficient. And besides that, in the recent past, we did a lot of technologies for the thin film and coating analyzer. So we can measure all these effects and properties that all these bulk material instruments can detect. We can measure that for thin films, for coating wafers, microchips as well. And that's where we are doing research in that, or we were doing research in the last years. And besides that, we have a lot of customizations, which makes Linzers a little bit different than our competitors. We do a lot of customization regarding pressure range, regarding temperature range. So we have ultra high and ultra low temperature versions of all these instruments, as well as pressurized options. And of course, we also have a customization, which is today's topic, which is the adaptation of corrosive and nuclear samples and atmospheres. Coming to today's topic, which is the thermal analysis of nuclear materials. I have to begin with the topic itself. So since the 1950s, the nuclear power plants are popping up all over the world, and it's one of the main energy sources all around the world. Even if Germany decided to abandon it and to focus on renewable energies, nuclear energy is playing a role globally, and there's still a lot of research going on. And meanwhile, there's reactor techniques of fourth and even fifth generation. And as said, there's a lot of research going on. This research includes the nuclear fuels, it includes reactor parts, it includes cooling media, and so on. And of course, whenever there is a building material or a new material, there is a need of research tools and instruments, and thermal analysis plays a crucial role. However, if you have samples that are more or less corrosive, explosive, toxic, or require high pressure or very dangerous conditions, handling and safety is a very critical point. The same for radioactive samples and radioactive materials, of course. If you have irradiation there, like if it's reactor components, even used reactor components or fuel rods or samples that are similar to that, there is a certain need of taking that into account when the instrument is designed. And for some toxic or explosive samples, it's maybe enough to focus on the sample chamber, but for more critical and more dangerous stuff, it might be useful to think about the complete instrument design, which we are doing, and that's the reason why we are doing that special versions. The challenge under that conditions is that in case of all these applications, it gets very tricky to operate the system safely, because to operate a system, usually you have to work with it, you have to touch it, you have to modify it by hand, and that's not always that easy. And to avoid any risk, the following points that you can see on the slide should be addressed. First of all, the system, of course, must be controlled from a safe place. That may be a glove box, that may be the neighbor room, or that may be just a fume hood. All the critical parts have to be accessed for maintenance and for operation, of course, so they must be accessible, either for the gloves, for your hands, or for robot arms if necessary. The samples must be placed in the system and removed from the system somehow safely, so that you can properly place it and remove it. And all components that are in touch with corrosive or radioactive irradiating substances, they must be able to withstand them. So the system must be able to withstand it. So your material must be selected properly. Our solution to address all these points is to split up the system. So if you have toxic or dangerous or radioactive environment, what we do, or what we try to do, is to separate the crucial parts that are needed from the electronics, from the accessory parts, from the control parts, and so on. That can be separated by a glove box wall. That can also be separated by even a concrete wall or a room wall. So you can control the system and maintenance the system from the next room, from a safe zone. That's our solution, how we address this. To be fair, we did not do that for all of our instruments and for the complete product range, but we did it for the most important ones. And what we did in the past and how we solved that can be seen on the next slides, beginning with the STA instruments. So first of all, for those who do not know, as I mentioned before, the STA is a combination of a DSC and a TGA, so a thermobalance and a calorimeter. Regarding the weight change aspect or the thermobalance, you need to know that in the base unit, so on the top left picture, you see how the instrument looks like in total. This is the standard bench top system. There is a furnace, an external furnace connected to a furnace lift. Within the furnace, you have a reaction chamber, and at the socket of the furnace, beyond the furnace in this platform, there is a balance unit. So we have that on this drawing here. You can see it. We have that balance cell containing a beamline balance that has a connector where a sample rod or sensor rod is connected, and on top of the sensor rod, you have the sample. This is going into the furnace. The furnace surrounds the sample and closes this chamber. And of course, the furnace consists of a heater and some insulation material. What the TG does is it monitors the weight change over temperature, or it monitors the weight change over time. So what you see is the sample weight and the change of sample weight during heating, during cooling, during whatever you do, maybe even isothermal. So that's what you get as a readout. On this right picture, you see how the instrument looks like if you remove the front panel. So there is this stainless steel housing, this base block where the balance unit is contained. And then you have some electrical feed-through, some connectors, and you have a connector for the furnace and so on. So this is how the STA looks like if the front panel is removed. The DSC signal is the second one you get if you have a simultaneous dynamic analyzer. Of course, the top of the sensor head. So I just said that at the top of your measurement rod, there is a sensor. In case of pure TGA, it's just a platform where you can put a cup or crucible with a sample. In case of TGDSC, the top of the sensor head looks like this. There is a DSC sensor consisting of two small crucibles. One is a reference that's usually empty. The other one contains your sample. And what the system does is it senses the temperature of the reference. It senses the temperature of the sample by using thermocouples, and it determines the difference in the voltage of the two thermocouples as a differential signal. You have to imagine, as long as the sample does not show any reaction and this complete sensor head is heated, both crucibles, both sides will be at exactly the same temperature. There will be no difference in thermal voltage between the two thermocouples. However, once the sample starts to react somehow, maybe a phase change, maybe melting, maybe reaction, the sample will consume or release some heat. And in that moment, the sample will be hotter or colder than the other side. And in that moment, you will have a differential signal forming a peak in the one or the other direction. Direction gives you an indication if this is an exothermic or endothermic process. Endothermic means the sample consumes energy. Exothermic would mean the sample releases energy, like if it burns or something. Out of this differential signal, you get these peaks over time or over temperature, and the area beyond the peak will even give you the amount of energy. So this is what a DSC does. Now coming back to modification, in the usual configuration, the benchtop version, you would have an instrument that will look like this on the top left picture. However, if you have a very corrosive or even radioactive sample, we try to separate all the electronics from the unit itself, leading to that concept you can see on the next slide. So what you see now is on the left side for the hot environment, the instrument is really reduced to the crucial parts. So you see at the bottom side here, the balance cell containing of a vacuum or gas connector. You have a flange for closing the furnace. You have this measurement rod and of course the sample, the balance chamber in here. You have the furnace lift and the furnace itself. And all the electronics, the main boards and the control boards, the control panels, the cables and so on are all removed. They are all put in these boxes you see on the right side. These boxes contain all the electronics, the control, the power supply and so on, and just a few cables needs to be connected to this unit, to this rudimental unit you see on the left side. So this is the real physical separation of all these critical parts that might require some replacement, some maintenance, except the sample rod. And this is what we can do. And this so-called normal environment, these control boxes can be placed in the next room. They can be placed outside of a glove box, like I showed you before. And that's what we did in the past. So this is our modification for the STA. And this can be even more adapted if it has to be controlled by a robot, loaded and unloaded. We can automatically fix this rod to make sure that the robot doesn't break it and so on. And there we also had a solution where this complete setup is operated by some automated robot systems. So this is what we did regarding the STA. On this slide, you can see an overview about options for that kind of STA version. So on the top left side here, you see again a picture of the real existing unit. That's the one that's placed in the hot cell. That was for one of our customers. You see, this is the rudimental setup. This blue part up here is the furnace. This column here is the furnace lift. This block is the balance unit, and all these cables are going through limo feed-throughs out of the chamber here. This setup, as said, can be ordered with Type C, Type S, Type K, and Type B thermocouples. These thermocouples are all meant for different atmospheres. It depends a little bit on the atmosphere you want to use and the temperature range you want to use. So out of atmosphere and temperature range combination, you can select the proper thermocouple or thermosensor for your sensor head. And on the right table, you see temperature range that we offer for that nuclear version. So we have DSC, TGA, and STA set up. And for DSC standalone, TGA standalone, and even STA, we offer low temperature furnace and high temperature furnace. So we can cover a temperature range from minus 150 up to 2400. I have to say, minus 150 would mean liquid nitrogen, which can be an issue if it's a hot cell. If you do not have access to liquid nitrogen, of course, we can start at ambient temperature and go maximum to 2400 centigrades with same resolution for all of these setups. So that's what we offer regarding the STA. Besides the classic STA, we also have a very special thermobalance, which is the so-called magnetic suspension balance that we also sold for one customer, which was the Department of Energy of the United States at Oak Ridge. They have a so-called magnetic suspension balance, which is a standalone balance, not an STA, but a balance, where you have, even if it's not in the nuclear version, you have already a separated sample reaction chamber. So the furnace and the sample chamber are already a closed chamber that is only in touch with the balance unit by a magnetic coupling. So you have a permanent magnet and an electric magnet that are in a levitating state. So the coupling is done via magnet, and the mass change is monitored by the move of this levitated part, and the balance unit is on top of this complete setup. So that's already a separation of beamline balance from the reaction chamber, and even there you can put it out of a glove box and the furnace with the sample chamber into the glove box. That can be seen on this sketch drawing on the right side. So this is what we already did for the already existing magnetic suspension balance, which is made for corrosive atmospheres. Just to mention that as a very special thermobalance. The next instrument series that's affected by nuclear applications that we did modify in the past is the dilatometers. Here we have the same concept. For those who do not know what a dilatometer does, usually a dilatometer is used for measuring thermal expansion. It also consists of a furnace chamber. On the picture here, it's the right part. And on the left part, you have a usually LVDT detector, which is, again, an electric magnet that is in touch with a push rod. And this push rod fixes your sample in a holding rod. And if the sample expands or shrinks, this push rod moves, and the movement of the push rod is recorded by the movement of this electric magnet. We have different versions of this kind of instrument. On the one hand, we have the classical push rod dilatometer. On the other hand, we also have already existing optical systems where we have, again, an enclosed reaction chamber in a furnace that has two optical ports, where we have a detection camera on the one side and a counter light or polarized light source at the rear side, which already gives you a certain amount of protection because the chamber is closed without the detector being in touch with the atmosphere. However, even here, we have a version that's made for nuclear applications. Yeah, the picture of that is, sorry for that, it's in the applications that we have at the end of the presentation. So again, as said, the concept is the same. We separate electronics more or less from the reaction and sample chamber. And yeah, the picture is missing, unfortunately. And here we have, again, some options. So regarding the diameter of your samples, we can go from 20 millimeters diameter over 10 to 7 down to 5 millimeters diameter of the sample. The length, the maximum length we can measure would be 50 millimeters. We have adapter for powders available. However, if you have toxic radioactive powders, it's very hard to load this powder container, to be fair, but it would be available. And again, we have a furnace program and a setup that allows measurements from liquid nitrogen range up to 2,800 centigrade. I know liquid nitrogen may be a problem, so you can go from room temperature up to 2,800 anyways. And if you allow liquid nitrogen, you even can go to liquid nitrogen range. So that's what we offer regarding the dilatometer. As said, there will be a picture and an application later when we look at the applications. For the moment, that's what I have to say about the dilatometer. I will now pass to Erica, who will introduce you the modified laser flash instruments.
Yes, so coming now to the laser flash instruments regarding the special applications. So first of all, I need some control over the slides. That would be helpful. Let's see.
I'm trying to, but it doesn't work.
Okay, then go to the next slide, please.
Yes, I will click it for you.
Great. Yeah, so here on the slide, for those who do not know, this is the basic principle behind a laser flash measurement. So we have on the one side a power source, which shoots a short and high intensity energy pulse towards the sample. The sample absorbs this energy, of course, within the material. It will be conducted, and a part of the energy will be also emitted on the rear side of the sample. This is an infrared light region, and this radiation we collect using an infrared detector. A typical signal which we collect, you can see on the right of the slide. So we have here a temperature rise with time, and out of this signal, we can find out the thermal diffusivity. For the thermal diffusivity, you see it in the upper block. There is a constant, it's a fixed constant. We need the sample thickness and the so-called half-time rise. The half-time rise is basically just the half of the maximum the temperature rise reaches, and here the timestamp is used for the calculation. Of course, typically one is not interested in the thermal diffusivity, but mainly in the thermal conductivity of a material, and to obtain that, one just uses the formula, which is on the bottom of the slide, where you can see that the thermal conductivity, the lambda, is the product of the thermal diffusivity, the density, and the specific heat capacity. Important is to know that all of these properties are temperature dependent. So in the ideal case, all of these properties are measured temperature dependent. The specific heat capacity, for example, can be determined either using a DSC, so a differential scanning calorimeter, or one can determine it also with the laser flash, but for that one needs a well-suiting reference material because it is a comparative method, and the highest accuracy you achieve with a quite similar reference material. On the next slide, you can see that the determination of this half-time rise is not as indicated on the slide before graphically, but there are some different models behind that. There are a lot of different models available, which are all considering different effects because, of course, like typical, reality differs from the theory. the theoretical model. So the theoretical model, the adiabatic one, differs in reality mainly due to two effects, which are heat losses from the sample to the surrounding or to the sample holder and so on, so that not all the brought in heat into the sample will be emitted directly on the rare surface, but might also go to the sides of the sample. The second effect, which causes non-ideal conditions, is the so-called finite pulse length effect, which happens especially for thin and high conductive samples, so that the laser pulse time, which is typically in a low millisecond range, has an effect on the measurement. For example, if you're measuring a sample of measurement time of 50 millisecond, then of course you cannot just ignore the 2 millisecond time of the pulse. And most of the well-known models consider either the one effect or the other one. What is very unique for Linsize is we have the so-called combined model by Dr. Dusa, which who invented a model considering both effects at the same time. And this leads to a very universal model, which can be applied to almost every material and makes data evaluation simple, as you simply can use this combined model for almost every material. And then on the next slide, you can see a bunch of different sample holders, which we offer for our laser flash system. On the left, you can see the sample carousels, so that we can load in up to 3 or 6 samples at the same time, so all can be measured in just one run. Typically, the samples are bulk materials, either round or square, ranging from, let's say, 10 to 25.4, so 1 inch millimeter diameter. This is the typical range, or they can be also square in a similar range of size. The sample thickness is typically around, let's say, 1 to 3 millimeter, but this, of course, can differ also for different kinds of materials. Mainly, the laser flash is designed for solid and bulk materials, but with some special sample holders, one can also measure, for example, liquids, and thus also maybe phase change materials, which are in the beginning solid and melt then at higher temperatures. So this is all possible within the laser flash, and you can achieve a high throughput. Let's stay on the slide before. Thanks. On the bottom of the left side, you can see a part of the sample preparation, which is mainly covering the sample with a thin layer of graphite. This we do just to maximize the absorption of the energy from the laser, to just put in as much energy as possible into the sample. And on the right side, you can see those sample carousels within the system. So on the upper picture, you can see even a part of the furnace. And now we can go to the next slide, which just summarizes the possibilities we have in modifying the system to be able to resist, for example, radioactive samples. So first step typically is to separate the main unit and the electronics. So to keep as less electronics within the main unit as possible. So for example, with the laser unit, one can use a fiberglass optical cable to just guide the laser beam towards the sample without having the main unit inside a glove box, for example, or in a hood. So the system will be also designed to be operated and also maintained in such a glove box, so that, for example, one can design parts to be grabbed with a robot, with a manipulator, or with gloves, so that you have a lot of flexibility in moving parts, and don't do them too small to be grabbed. For example, also for high temperature applications, going up to 2000 degrees Celsius or higher. We have some special furnaces out of tungsten or graphite. And one important part is that the detector collecting the temperature rise with time can either be cooled with liquid nitrogen, but this is often a problem in glove boxes. So we have also an option which is thermoelectrically cooled, the so-called Peltier cooled detector, so that one does not need liquid nitrogen to be used inside the glove box. Especially also for the high temperature application, we still have a sample robot, so that depending a little bit on the configuration, one can measure also up to 3 samples at the same time, up to 2800 degrees Celsius. And the sample robot is especially useful for the CP measurement mode, as a DSC measurement method typically limits the determination up to 1000 degree. For higher temperatures, one either need another method or one can use this comparative method by laser flash. And as mentioned before, the accuracy depends strongly on the compatibility within reference and sample, and also on the measurement conditions. So the more similar reference and sample are, the better the measurement is. And of course, it's very helpful if both of them are measured under the same conditions. And this can be realized with the sample robot, as both are measured at the same run, at the same temperatures within the exact same atmosphere, and so on. On the right, you can see, rough overview over the models we have, listing the different furnaces. The main difference between the LFA 500 and the LFA 1000 is the source of energy. So within the LFA 500, we use a xenon lamp as energy source, and the LFA 1000 uses a more powerful and more flexible laser source. But both of them have different options of furnaces, so lower or higher temperatures, even to subambient temperatures. One can go using liquid nitrogen, and a special series is the LFA 2000, which is the high temperature applications above 2000 degrees Celsius, and these use also the laser. And all of these models can be used within different atmospheres, mainly the laser flash method. Measurements are done in vacuum, or for example, in inert atmospheres. These are the mostly used atmospheres. On the next slide, you can see some examples of special laser flash configurations we already built, just to point out the flexibility and the many options one has to modify a system to the needs. On the left, you can see the tungsten furnace we built, which can measure up to 2400 degrees Celsius. And you can see that the system is, let's say, very naked, so that most of the electronics was removed to be placed outside, on the outside of the cell, to be not close to the sample. Below that, you can see the measuring system, so the sample holder of this tungsten furnace, and in this case, the sample holder just carries one sample, because in this case, a high throughput was not necessary. On the upper right, you can see a very special model of the Laser Flash 500 series, so a laser flash with a xenon lamp as a power source. Here in this case, we had to put the system in a glove box with very limited space. So we had to completely redesign the system to be able to fit in there. And also the unit was separated into 3 parts, because on the one hand of the space, so we had not very much volume to the top and had to stay on the bottom. So we completely separated the parts, and the big box, which you can see on the right and the back, is the the condensator bank for the charge voltage. So the capacitors are built in there, and this is connected by the part in the front, so the so-called power rail, to be able to transport the charge towards the light bulb. On the bottom on the left, you can see a laser flash 1000, also designed for a nuclear application. Here, the special part is that the system is equipped with two furnaces, so that one can cover two different temperature ranges, and one can benefit of the different advantages of a furnace. For example, some allow a very high heating rate or just very high temperatures, and with that you can also maximize the throughput. On the bottom right, you can see an example of a sample holder, which was specially designed to be able to be handled with a manipulator, so with a robot, so that we sharpened a little bit the edges so that the robot can grab them easily, open and close the sample holders without much effort. And in this case, the sample holder is made out of stainless steel. Typically, the sample holders are made out of graphite, but in this case, this was not allowed in the glove box, so that everything was designed out of stainless steel. Okay, that's all for this slide. And this just summarizes it a little bit. So with our flash systems, we have the xenon-based and the laser-based system, the LFA 500 and 1000. Offering a broad application range from low to very high temperatures. And we have a lot of flexibilities regarding the detector, the furnace, and the power source, also the sample holders. The picture which you can see in the middle is the sample holder for the LFA 2000 series with the 3-sample container, where the complete sample holder is made out of graphite. And on the right, you can see a screenshot of our software where you can see an example of such a temperature rise curve, which in this case has a very ideal shape close to the theory. Okay, so that's all about the laser flash system. Now we come to some applications, some example measurements we already did in the past referring to nuclear materials.
Yes, I will just take over from here. So I just picked a few samples that were measured. First of all, this is a thermobalance application that is a measurement of titanium hydride or hydrogen adsorption and desorption on a titanium surface in argon atmosphere. In that case, these customers were investigating titanium components of a reactor that were able to take off some hydrogen, and they wanted to investigate before and after the use if this capacity of adsorbing and desorbing hydrogen changed. This is just one of these measurements. So what you can see here is this blue curve, which indicates the mass loss over temperature, and a red curve, which indicates the heat flow as a DST signal. What was done exactly is there was this titanium surface. It was a porous surface. It was seeing hydrogen at lower temperatures. Then the hydrogen was stopped. It was replaced by argon flow, and then the sample was heated. The sample therefore took up some hydrogen. It adsorbed hydrogen, and during heating, it started to release it at 300 and 400 centigrades in a 2-step process. These guys repeated that step after this material was used to see if the porosity increased and the hydrogen absorption was bigger or lower after use, and that was the purpose of that kind of analysis. Another measurement example, which I got from one of our customers from Brookhaven, who has one of these radioactive dilatometers, if I may call them like this. They were investigating influence of irradiation on super-invar alloys. So what you can see on the picture is this is the dilatometer. On the right side, you see the detector part. On the left side, this black part is the furnace with power cables going to a feed-through out of a hot cell. and then you see manipulators or robot arms, however you may call it, to load and unload samples. As said, the dilatometer measures the thermal expansion and determines the coefficient of thermal expansion. And what they did is they used irradiated, medium, and high irradiated samples and compared them to non-irradiated samples and looked at the thermal expansion. So the samples were heated linearly, and what you see here is different curves with different expansion rates. And what they found is that the irradiation level, the sample or the INVA superalloy sees, has direct influence on the thermal expansion. So the expansion rises, or the coefficient of thermal expansion rises by irradiation for that kind of alloy, which is a quite important and very interesting observation. That's what they did. They also made further investigations and also saw that the coefficient of thermal expansion is directly dependent on the amount of displaced atoms. So radiation causes displacement of atoms, and the more atoms of the alloy were displaced, the higher the CTE got. So that's what they found with the study using our dilatometer. Finally, we also have an application for high temperature thermal diffusivity measurement with the LFA. So in that case, graphite was measured using one of the modified LFA instruments up to 2800 centigrade. It was a LFA 1800. It was a high temperature system. And this complete experiment was performed in helium atmosphere, as Erica just described. At each of these temperature points here, there was a measurement. So you heat to the next temperature, do the measurement, heat to the next temperature, do the measurement, and so on. This is why there are so many points, and there's not just a line, because each point marks one measurement or one experiment at the given temperature. And what you can see is the thermal diffusivity and thermal conductivity behavior up to 2800 centigrade using one of the nuclear LFAs. Then we have an application about molten salts. Maybe Erica says some words about it because I did not do it by myself.
Yes, so this example shows a very special application. So here a phase change material was used. At the beginning, at room temperature, it was solid and melts at higher temperature. So for that, we use this special sample holder for liquids and powders. And the measurement procedure was the following. So the sample was put inside and heated up a little bit above the melting temperature. At this temperature, it was kept for a couple of time. Then sample was cooled down again, and this process was repeated a few times to remove all the air inside the material and to ensure that there is a good contact between the material and the sample holder, because the brought in heat will be transported from the bottom to the top, and of course there should be a very good contact to have this heat conduction as best as possible. On the right you can see the design of the sample holder, also with a cut through, where you can see in the middle the volume where the sample will be located. Due to a fixation of the lid, the distance between the bottom and the top of the sample holder is fixed to 1 millimeter. And on the sides of this, we have some excess volume for the case that the sample starts to expand at higher temperature, so that the sample doesn't spill out of the sample container. On the left, you can see then the results of the measurement after this preheating to remove all the bubbles and have a good contact. And you can see also that the thermal diffusivity was recorded. And out of this and the specific heat capacity values which were obtained using a DSC, the thermal conductivity could be determined. The complete test and also the preheating was performed in a helium atmosphere, enhancing just this measurement of such type of sample and also this type of sample holder. So yeah, so this shows just an application of a molten salt, which is typically used in the so-called molten salt reactors.
Yeah, and coming to the last slide here, as said, we just picked some interesting applications that you get an impression of what we did in the past. This slide shows you the most important customers who already own some special modified instruments for nuclear application. As you can see, there are multiple famous institutes and research centers beyond them, among them, sorry, and some of them even got more than one instrument. This would be the end of our today's presentation.